Hello everyone, welcome to Open Class. My name is Shanjida. I am currently a second year human bio student at UFT, and today I'll be going over some commonly asked chemistry questions, both at the high school and college/university levels. If anyone needs an additional help with schoolwork or needs tutoring, please check the description below. And other than that, we will just get right into it. And so our first question for today says, what is the molar mass of carbon monoxide? Right, so carbon monoxide consists of one carbon and one oxygen, and in order to find the molar mass of this compound, we can break this down to first find the molecular mass of the individual elements. So the molar mass of carbon is, the molar mass, to find the molar mass, it's given in the periodic table. So the molar mass, just a side note, molar mass is basically the same thing as the atomic mass of the element. Atomic mass, and as you know, atomic mass is denoted as AMU, right? So it's basically the same thing. So if we go to our periodic table over here, so we can find carbon, and so carbon is basically, so since it's 6, so the molar mass consists of the addition of protons and neutrons. So basically it has 6 protons and 6 neutrons. So like the molar mass would be approximately, I'll just round it, it's gonna be around 12 grams per mole. Okay, and so if you go back to our question here, it says what is the mole. Now we have to find the molar mass of oxygen. So the second step would be to find the molar mass of oxygen, and so this is near, so we can find oxygen here, and it's over here. It says the number of protons here is 8. So basically we have the same number of protons and neutrons. So it's gonna be approximately, let's say, 16.0 gram per mole, right? And then in order to find the molar mass of CO, we're just going to add these two values, and so what we get here, the molar mass of carbon monoxide is approximately, and if you add these two together, you get around 28.0 grams per mole. Okay, and this is, yes, so this is what they've got. This is correct. Okay, so our second question says, what is an anabolic reaction? And so an anabolic reaction, so number 2, an anabolic reaction, when we're talking about anabolic reactions, we're actually talking about the main reaction, which is called the metabolic reaction. So the main type, it consists, so this metabolic reactions, right? And so the metabolic reactions consist of 2 categories. They are made up of anabolic and catabolic. Okay, so in this case we're talking about anabolic, but anabolic and catabolic, they work together to function our metabolic reactions in the body. And so I'll first address catabolic. So the catabolic reactions are reactions that break down large molecules into small molecules. So for example, so I'll just say, so break down like large molecules into smaller molecules, right? Smaller molecules. So for example, what we can say here is, for example, the glycolysis pathway. For example, glycolysis. This right here. Okay, for example, glycolysis. And if anyone doesn't know what glycolysis is, this is a reaction where glucose, which is basically a sugar, is broken down into pyruvate. So a glycolysis is a pathway to make basically ATP, our energy, where we get our energy from. So so this is, for example, glycolysis is a pathway. Where glucose is a sugar molecule, and it's really big. Or glucose. This is basically a 6-carbon molecule, so 6 carbons. So you can imagine it's pretty big. Glucose, where glucose is broken down to pyruvate, which is another molecule, down to pyruvate. So pyruvate, it's way smaller than glucose, and so this is what a catabolic reaction is. And then when we're talking about anabolic reaction, right, this is so anabolic reactions are building reactions. So it's basically the opposite of catabolic, where you're actually making a large molecule. So you're making a large molecule from smaller molecules, right? So it's basically the opposite of catabolic. So you're making larger molecules from small. Okay, so this could be, you can literally reverse this and just say that you're making glucose from pyruvate. So for example, make glucose from pyruvate. Okay, and so this is just okay. So this is what an anabolic reaction is compared to catabolic. So they are used interchangeably, whereas our body functions this way. So we use catabolic and anabolic reactions. And okay, anabolic reactions are building up reactions. So yes, this is correct. Okay, so 3. So this is where we're talking about, so our third question says oxygen gas O2 has a molar mass of about 32 grams per mole, and hydrogen gas H2 has a molar mass of 2 grams per mole. Calculate A, the RMS speed of an oxygen molecule when the temperature is 300 Kelvin, and B, the RMS speed of a hydrogen molecule at the same temperature. Okay, so what we're dealing here with is room mean square speed, RMS. So this is the average molecular speed, and so I'll just write here RMS, or we can say U RMS, right, is the average molecular speed of an element, basically. Okay, and this is the equation is given by U RMS. The equation is given by U RMS is equal to the square root of 3RT over M, where M is the mass, basically. So R is the ideal gas constant, which is 8.314 joules per mole Kelvin, mole times Kelvin, so this is a multiplier, mole times Kelvin, and T is the temperature in K, temperature in Kelvin, so C, okay, and M is the molar mass of the gas, sorry, of a gas. So where M is the molar mass of the gas. Okay, and so basically what 1 joule, so J is for joule, is equal to 1 kilograms times meter squared over seconds squared. Okay, so this is the basic units. This is what we're talking about, speed, right? And so this is basically the conversion unit. You can just keep this in mind. And then, so now when we're solving for the speed for O2 in this case, so let's just say O2, right? We're going to use this equation of U RMS is equal to the square root of 3RT, this is a T, RT over M, and then we're just going to substitute what we know. So this is A, this is question A, and so we're just going to substitute the values of what we know. So we're given that the temperature is at 300 Kelvin, and we have the gas, the ideal gas constant, and so we're just gonna plug in the value here. So I'm just gonna write it over here. Okay, so I have room, so square root 3 times 8.314 okay, times 300 K. Okay, I forgot to put I just put the units. 3.4 joules per mole Kelvin times 300 Kelvin over the molar mass, which is given, that is 32.0 grams per mole. And so what we're gonna do here, since this is in gram per mole, how about I'll just actually we're gonna convert this into this factor here, 1 kilograms meter square per second squared, because it would be easier for us that way. And so we're just gonna convert, so we have to convert both the denominator and the numerator. And so in this case what we have is kilograms per meter squared over second squared, and so 32.0 grams per mole. And what we're gonna do here is convert the units. So 1 kilogram, since 1 kilogram is equal to 1,000 grams, so we're just gonna write 1,000 grams, okay? And so over here, these two get cancelled out, and then what we're left with, and so if we just do the whole math here, which I guess we can all do, and then the answer basically in this case would be around approximately 483 point, let's say 6 meters per second. Okay, and then so the RMS for oxygen gas is 48.36 meters per second. And then, so this is what we got for O2. And then for question B, it says to find the RMS speed of hydrogen gas. So to do this, we basically do the same thing. We have the room mean square of hydrogen, which is, the formula is 3RT over M. And so we're gonna just put everything we know here, and what we're gonna get is mean square root of 8.314. I'm still using the kilograms meter squared over second squared in this case also, times 300 Kelvin. Okay, and over, so it's given the molar mass of hydrogen gas is and we're also going to convert this to 2.00 grams per mole, and we're going to multiply this by 1 kilogram over 1,000 grams. Oops, I should mention this, that it's not just the this is, so the whole thing is getting square rooted, not just the numerator. And so when we square root this whole thing here, so when we square root this, we basically get an M and a so we get meters over seconds, since the square gets cancelled out by the root. And so that's how we get, and if we do the math here, we will get approximately 1,934.2 meters per second. And so since the kilograms over kilograms get cancelled, and so you're left with basically just meters per second. And so this is the answer for hydrogen gas, the RMS for hydrogen gas. Yes, okay. is correct. Good job. Okay, for question number 4, it says, what is the molar mass of C3H8? Okay, so to find this, we will again have to use, so this we were gonna have to use the periodic table to find the molar mass of the individual elements here. And so molar mass of C3H8. Okay, so C3H8, just to add, it's called propane, and this is how it looks like structurally. So this is H. So this is called propane. Okay, and so, or it could also look like 1, 2, 3, basically like that too. And so in order to find the molar mass of this, let's find the individual molar masses of the elements. And so first off, let's look at carbon. Molar mass of carbon is approximately 12.01 grams per mole, and again you get this from the periodic table. And since we have 3 carbon atoms here, we have to multiply this by 3, and so what we get here is around 36.01 grams per mole. Okay, and then our second step would be to find the molar mass of hydrogen, and we have 8 hydrogen atoms. Okay, and so the molar mass of hydrogen is basically 1.01 grams per mole of one hydrogen atom, that is. But since we have 8, we're gonna multiply this by 8, and what we get here is approximately 8.08 grams per mole. This is supposed to be this is supposed to be 0.3 grams per mole. And so what we're gonna do here, the next step, is the molar mass of C3H8, also known as propane, is approximately, so you just add this whole thing together, 108. You're just gonna add 36.03 plus 8.08 grams per mole. We'll just write this neatly. Okay, so molar mass of C3H8 is approximately 36.03 grams per mole plus 8.08 grams per mole. Okay, and what we get here is approximately 44.11 grams per mole. Also to mention, I just round these two numbers, but I suggest using the periodic table to find the exact molar mass, and just using that to calculate the exact molar mass. But this is basically the same thing I've got. It depends on the question. If they're saying the exact, so we use like all the numbers and behind the decimals. and get the exact molar mass, but I just rounded it here, so this is also the correct answer. Okay, fourth question. What is the structure of urea? Okay, so urea is urea. So urea is a waste product, basically, of humans. Okay, it's basically what the waste products from humans. Basically, it is known as carbamide also. This is list. Is a waste product from humans, basically. It is also known as carbamide. It's an organic compound with the chemical formula of CONH2 bracket 2. Okay, and this has an amide group. As you can see, it has 2, so it has two amide. Groups. It has 2 amide groups. So this serves as an important role in metabolism and of nitrogen capturing compounds by animals. And so the formula for this chemical structure for this is basically, it has a double bonded O. So it's basically NH2, NH2. So we have our 2 amide groups. It has a carbonyl group here. So these are the 2 functional groups. Carbonyl group. Okay, and so yeah, this is the structure of urea. This is correct. Okay, 5. How many ounces? Okay, so how many ounces are in 500 ml? Okay, so basically, so we're trying to convert how many ounces are in 500 milliliters. So what we're trying to do here is go from milliliters to ounces. So what we can say here is to find, so the basic step to do, the first step to do is find in 1 milliliters, how many ounces are there. So 1 milliliter is equal to basically how many ounces, right? And so to do that, there's a basic converting, so this is actually given, and so this is 1 milliliter is basically equal to 0. So this is from scientific, this is found scientifically, basically is just known for ounces. So OZ stands for ounces, the scientific unit. And so to convert, so you can imagine that 500 ml is equal to 500 ml. So to get ounces, we're just gonna multiply 500 ml times 0.033814 ounces, and what we get here is we get around approximately 16.9 ounces. Okay, and so therefore we can say 500 ml is equal to 16.9 ounces. Yeah, this is correct. Okay, so 6. Draw the Lewis structure of ammonia borane. What are the formal charges on each of the atoms? The strong molecular forces of attraction must be the result of the high polarity of the boron to nitrogen bond. Okay, so ammonia borane, right? Okay, so the ammonia borane structure is basically like this. So we have our borane and ammonia. So ammonia, I'll just address ammonia is NH3, okay, and then boron is just B, right? And so to draw this structure, what we're gonna have is our boron and our nitrogen in the middle, and since it's ammonia and nitrogen has 3 H's, and so so it has 3 H's, and so our boron also over here would have 3 H's. This is what it makes ammonia borane. So this is ammonia borane. Okay, and now we're talking about formal charges, and so you can see that to get the formal charges, we need to see basically how this is formed. So recall that nitrogen has 5 valence electrons and boron has 6. Has 6 valence electrons. Okay, so you can, from here, if we find boron, it is a non-metal, of course. Same goes for nitrogen, and so this attraction here would be polar covalent. So the bond between we also have to look at the electronegativity, and it would be, since boron is around 2 point something and nitrogen is around 3.4, So the bond between boron and nitrogen is polar covalent. Okay, and in order to find the charges, we have to look at the structure here. So if we were to break the structure, and I'll just rewrite it like this, N and nitrogen. Okay, and so boron is H. So you can see how boron's outer shell is basically filled, whereas nitrogen still has 2 valence electrons left, and so it can make another bond, whereas boron cannot, because it basically it's filled its outer shell. And also recall the octet rule, right? So basically, I don't know if you guys know, but nitrogen is one of those few elements where it does not follow the octet rule, so it doesn't have a full octet. It will never have a full octet. Basically, nitrogen doesn't follow the octet rule. Okay, so it can make as many bonds, basically. Not as many, but like I guess 11 bonds. And so to follow the formal charge, the easiest way we can do it is say that since boron cannot make another bond, but it has to, so it's gonna share the electrons here basically, but so it's basically gaining electrons, right? Whereas nitrogen is basically kind of donating them to boron, and so boron has to make another bond with nitrogen, so it basically has 4 bonds, so it's sharing 2 electrons here, so it gains a negative charge, right? Whereas nitrogen basically is just donating them basically, so this is why nitrogen is basically positive here, and boron is negative. And so this is why the formal charges of N and B is +1 and -1. So this is correct. Okay, the solution is correct. So, okay, what is the specific heat capacity at constant volume of nitrogen gas? So the molar mass is given, and so we have to find basically the heat capacity. Okay, so I'll just write molar mass. So I'll just write now what we're given. Molar mass of N2 is, it's given 28.0 grams per mole. Okay, and so we're trying to find the heat capacity at constant volume. Okay, so what we can say here is specific so our specific heat capacity is equal to molar heat capacity over molar mass. Okay, and so the molar mass of a diatomic gas, which is N2, is given, and so the molar mass is given, and so the molar heat capacity for basically a diatomic gas, which is like N2H2O2 F2, is basically, since it says it's constant volume, so we're gonna use the formula 5R, right, over 2. So where R, we call that R is our ideal gas constant, and this is 8.314 joules per mole Kelvin. Okay, and so what we're gonna do here is basically so back to our specific heat capacity, right? We have our molar heat capacity, right, 5R over 2, and we're just gonna divide that with our molar mass, which is 28.0 grams per mole. And so specific heat capacity is equal to, so we have 5, so I'll just 5R over 2, 5R over 2, this is all over the molar mass, okay, and so so I'm just gonna do 3.14 joules per mole kilograms over 2, and this is all over 28.0 grams per mole. Okay. However, we can also like cancel this out, and we have 2.5 8.314 joules per mole Kelvin times Kelvin over 28.0 grams per mole. And so if we do the math here, we will approximately get 0.742 joules per gram kilogram. So the moles get cut out here. So the moles get cut out, and we're left with grams per K. And so if we want to not have decimals, we can just multiply this by 1,000, right? And so what we get here is 742 joules per kilograms times Kelvin. So specific heat capacity, so the specific heat capacity of nitrogen gas is 742 joules per kilograms Kelvin. And so yes, so this is what we get. So this is correct. Okay, so second question says, what is the mass number of oxygen? So mass number, they're talking about molar mass. Okay, to find the molar mass, we look the molar mass. So molar mass is molar mass of an element is equal to the atomic mass number. Okay, where the atomic mass number consists of neutrons and protons. Okay, so you just add the protons and neutrons together, and protons. Okay, and so for basically oxygen, so if we look here at our periodic table, oxygen has 8 protons basically, and it also, so our normal oxygen compound has 8 protons and 8 neutrons. So basically we just add, so oxygen, so we'll just say molar mass of oxygen is basically 8 protons plus 8 neutrons, which is basically 16 grams per mole. So the unit for molar mass is grams per mole. So the molar mass of oxygen is 16 grams per mole. Yes, this is correct. Okay, what is the molar mass of magnesium? So this is the same thing as we're saying that molar mass of magnesium. So when we're trying to find the molar mass of magnesium, right, we are trying, so it's basically equal to the atomic mass of energy of magnesium. And so the atomic mass equals to the number of protons plus the number of neutrons. Okay, so if you look at our periodic table over here, magnesium is right here, and we see that magnesium has 12 protons, and likely it does have 12 neutrons, and so we can say that 12 plus 12, right, is equal to 24 AMU. So the unit for atomic mass is AMU, but it's also the same thing as saying grams per mole. So we can say that the molar mass of magnesium is equal to 24 grams per mole. Yes, so it's around there. This is correct. Okay, so our 9th question. It says, what is the structure of toluene? Okay, so toluene toluene. Okay, so I'll just write this. Okay, it's basically an aromatic hydrocarbon. So it's an hydrocarbon. It consists of carbons and hydrogens. It is colorless, so it's an hydrocarbon. I'm just giving some background information about this hydrocarbon. It's colorless. It's very water insoluble, so hydrophobic, basically water insoluble. And so basically, to the structure of this is, so we have so I'm just gonna draw an aromatic ring, and so it has double bonds, and it also has a methyl group. Okay, so this is also known as methylbenzene. So this is your benzene, this is your methyl, so this is methylbenzene also. So it consists of a methyl group on the first carbon, basically, or so over here, basically, whichever starting carbon you want to take, and it's a benzene ring also, a benzene structure. And yes, this is correct. Okay, so our 10th question says, what is a Newman projection? Okay, so a Newman projection is a way to basically visualize the conformation of a structure or of a chemical bond, basically, from the front. So like you're looking at it from the front to the back. So basically we have, let's say we have a structure here. So let's see, what is a Newman? What is a Newman projection? Okay, so basically you're visualizing the conformation or the structure of a chemical bond from front to back. So let's say you have so the structures are basically drawn like this, right? So let's say, so we have this, right? And then I'm just gonna draw this, and so you have, so then you have, so this is the back, so let's use a different color here. Okay, so this is basically the back, this is the front, right? And imagine that this is your eye, right? You're looking at it from here, basically, right? You're looking at it from here back. And so to draw a Newman projection is basically, so you draw this like this. So you have a big circle here which denotes the carbon. So this is basically the back of the carbon, and so you have, this is a red dot here. So this red dot represents the back carbon, okay? And so you have back, okay, so and then you have, so you're gonna draw the front, right? So this structure here, and so what you're gonna do here is you're just gonna, so it has to be straight, okay? So it's gonna, so you're gonna first draw the front part of it, and then the back is basically you're just drawing this part, and so it's basically just like this. Okay, so this is your Newman projection, and of a chemical bond basically. So Newman projection. Okay, and yes, it's called a Sawhurst projection, and this is correct. Okay, so our next question says, how do you convert grams to moles and moles to grams? So another converting question. So the number of moles basically of a substance can be figured out by dividing the mass in grams by the molar mass of the substance. So what I mean by this is to find the number of moles, right? So if you recall that, so I'll just write side note, just write this first. If you recall, right, if you have our molar mass unit is basically grams per mole, right? So we're trying to find moles here. And so if we rearrange this equation basically, and grams is our mass, right? If we rearrange this equation, we can just multiply moles on both sides. Okay, so I'm just trying to show the full-on steps on both sides. And what we get here is mole times molar mass. So this gets, cancelled out, and you get grams. And so if you want moles by itself right now, we're gonna take the molar mass to the other side, and the result would be division. So our mole is basically equal to grams per molar mass. Okay, and so this is basically the same thing as saying grams per mole per gram, right? And so you can rearrange this equation also. So over here we already found how to get grams, so it's basically moles times the molar mass. And so this is how you basically get grams, and this is how you get moles. So you just need to you need to have the molar mass, the moles, and the grams to find either any of them. And so yes, this is correct. And so that was the end of our session. If you like this Q&A, please like and subscribe to this channel and hit the bell icon whenever you want to get notified if we upload a new video. Other than that, if you have your own personal questions, there are links down below and you can follow them and ask your questions. Other than that, this is Shanjida, and I'll hope to see you soon. Bye bye.